Hi everyone. So in this video we are going to compute the electric field from a rod on the symmetry axis. So on the screen you could see a rod which is electrically charged. So the charge is uniformly distributed across the rod, and we are going to compute the electric field due to this rod at the point P. So let's get started. In the previous video we found out that the electric field due to a continuous charge distribution is calculated using the formula electric field equals the integral of k dq, which is dq, where dq is our infinitesimally small charge, divided by r square, which is the distance between the charge, the source charge, and the point, and r unit in the direction of r unit vector. Okay, so in this video I'm going to compute the electric field of this electrically charged rod. So let's do that. First of all, you need to identify r. Now I'm going to first of all identify my coordinate axis. So my this axis, this distance is y here, and this is a rod of length L. So since this is my origin, this is going to be minus L over 2. The length of this part is going to be minus L over 2, and the length of this part is going to be plus L over 2. Okay. Yeah. So now I'm going to identify my unit vectors, my coordinate system. So my unit vector in the x direction is I unit vector, and in the y direction it's a j unit vector. Okay, before I calculate the electric field and talk about it, I'm going to talk about my integration variable here. Since this is a continuous distribution, each infinitesimally small element of charge, which is dq, will have a contribution of electric field at point P. So the thing which is changing is the distance, is this horizontal distance, and I'm going to represent this horizontal distance with x. So if for example my charge is of this part, so this will have a distance maybe x1. The charge at this part will have a distance x2. So the thing that is changing is my distance x. So I'm going to say that x is my integration variable. Okay. Okay. So now we know what x is. Let's find out my distance r, because I'm going to deal with this unit vector and this distance r. Okay. So now, since at the origin till point y, my vector is r p unit vector, and from the origin till the source, I'm going to say that my vector is r s unit vector. So if I now need to find this RSP, which is the distance from the source till the point, I'm going to call this RSP. How will I find that? This is a vector, so I need to go up by RP, and then I need to go to the left by RS. So this is going to be RP vector minus RS, because this is now in the negative y direction, negative x direction. So this is going to be RS. So my RSP is going to be RP vector minus RS vector. So this is how I will denote my distance. Now let's talk about RSP unit vector. So unit vector is the vector divided by its magnitude. So this is going to be RP minus RS divided by the magnitude RP minus RS. Now let's compute RSP here. So RSP is equal to, what is my RP? This is y in the j unit vector direction, so this is going to be yj. Then RS is my x in the I unit vector direction, so this is going to be xi. So then RSP unit vector is going to be yj minus xi unit vector divided by, now look here, I have the hypotenuse here. This is my right angle triangle. I have my base, I have my perpendicular, and I have my hypotenuse here. So this is going to be under root x square plus y square to find the magnitude of hypotenuse. So this is my RSP unit vector. So now I know what my unit vector is, and I know my distance is. Now the thing which I need to talk about now is this dq here. In the previous lesson we covered charge densities, and since I have a rod here, so the charge density I'm going to talk about is linear charge, line charge density, which is represented by lambda. So lambda is equal to dq over dl, or since I am talking about dx here, so this is going to be dq over dx. So that means that dq is equal to lambda into dx. So I can replace this dq by lambda dx, and lambda is equal to q over l, which is the total charge divided by the total length. So I can also substitute this here, and my dq will now become q over l into dx. So now I have dealt with the direction vector, I have dealt with the distance, I have dealt with the charge. It's very easy to compute the electric field at the point P. I'm going to just rewrite my formula here, and let's compute it now. Now this R is going to be RSP squared, RSP unit vector, which is going to be RSP squared is going to be so this is RP minus RS squared into the unit vector, which is going to be yj minus xi divided by RP minus RS. This will now become dq divided by RP minus RS cube into yj minus xi unit vector. Now since the magnitude Rp minus Rs is equal to under root x square plus y square, I could just simply replace that here, and this is going to be x square plus y square to the power 3 over 3 by 2 y into j unit vector into xi unit vector. Now let's talk about an interesting point here. So due to symmetry, I know that my electric field at point P by the left side is in this direction. My electric field at point P by the right side, by the right element dq, is in this direction. If I break this electric field into x and y components, I can see that my x component are going to cancel out, and the only electric field effective at point P is my y component, is due to my y component. I'm just going to erase this from here. So the direction of the net electric field will be in the j unit vector direction. So by this, I know that my xi part is basically just going to be 0. I can just like write this here. So this is going to be k dq over x square plus y square to the power 3 by 2 yj unit vector minus k dq over x square plus y square 3 over 2 xi I unit vector. So we know that due to symmetry, my x component is going to cancel out, so this will reach 0, and the only effective component at point P is in my j unit vector direction. Now I can replace this d cube with q over L dx, which we have done before, x squared plus y squared to the power 3 over 2 y into j unit vector, and where my limits are going from minus L over 2 till L over 2, and I can take out the constants, which is going to be k, q, L and y, and then I'm going to integrate it from L over 2 till minus L over 2 dx divided by x squared plus y squared 3 by 2 in j unit vector direction. So this is how we are going to compute this. Now we can just easily solve this by adding the right values in this integral, and this is how we calculate the electric field due to a rod on the symmetry axis.